Okay, so in a half hour we're going to hear a live streaming of a press conference at the National Science Foundation headquarters, at which there will be some announcements of some exciting new results in neutrino astronomy and multi-messenger astronomy. But before we start that, we thought it would be helpful to provide some context. So IceCube is a neutrino observatory, which many of you are familiar with, which is headquartered here at the University of Wisconsin. And it's a project which sort of spans physics and astronomy topics. And so we're going to provide some context and some perspectives from both physics and astronomy. My name's Justin Vandenbroek from the physics department here on campus. I'll explain the IceCube Neutrino Observatory. Lost the link. Can someone help from... Okay, so IceCube spans the physics and astronomy fields, and so we're going to provide some context both from physics and astronomy. Again, I'm Justin Vandenbroek from the physics department, and I'll explain sort of how the detector works, especially the history of leadership from the University of Wisconsin of neutrino astronomy and of this detector, the IceCube Neutrino Observatory. I'll then hand it over to my colleague, Jay Gallagher, from the astronomy department, who will provide some context, some scientific context from the perspective of astronomy.
Justin, maybe you should explain what's on the table here.
Okay. Great idea, Jay. So this will give you a head start on the exam later. This is called a digital optical module. It's basically a large light bulb in reverse. So a light bulb converts a current into a light. This basically converts light into a current. And so it's a sensor of light. It can detect such faint light that it can detect individual single photons. So if a photon, you can't see it from the audience, but if a photon hits the bottom of this sphere, there's a very sensitive surface in there, and that surface converts that photon of light into a little pulse of current. And then there's basically a computer here which collects and digitizes that signal and then has digital communication and power to the surface. So we have over 5,000 of these sensors that are buried in the ice in Antarctica at the geographic South Pole. Any other questions before we get started?
How many domes are in IceCube?
Over 5,000. So they're inside the ice. There are 86 individual strings. Each one is 1.5 miles deep, 2.5 kilometers deep. Each one has 60 individual ones of these sensors. So it's a very robust technology for such a harsh environment. It was constructed... All right, here we go. I'll come back to that. I'll come back to that topic. Okay, so the field that we're talking about here is multi-messenger astronomy. So what is multi-messenger astronomy? In my personal opinion, it's a new topic which is revolutionizing astronomy. And the basic idea is that for hundreds, for even thousands of years, humans have done astronomy using different types of light. But only in the last few years are we able to use other messengers in addition. So cosmic rays, gamma rays, and now neutrinos, and of course also gravitational waves. So what's going on here? A lot of you are familiar with the Large Hadron Collider. It's the largest, most energetic particle accelerator humans have ever created. It's a huge triumph of humanity, and yet there are even more energetic, even larger hadron accelerators throughout the universe. We know that not because we've actually seen those accelerators directly, or maybe we have, but we don't know what they are yet. We know it because we detect the hadrons themselves. And so when energetic hadrons from the cosmos reach us at Earth, we call them cosmic rays. So here's an example. A proton would be a simple example of a cosmic ray. It's been produced by this Large Hadron Accelerator, and it's traveled through the universe. The problem is it's been deflected by magnetic fields. So when we detect it from this direction, it's not associated with the actual source that it came from in this direction. And so instead of using the hadrons themselves, the cosmic rays, we can also use gamma rays. So we know that individual cosmic ray sources should produce gamma rays in addition to cosmic rays, and so we can detect those gamma rays and use them to identify the sources. The challenge with gamma rays is that they're actually absorbed by light. It's this amazing fact. It's like if you shine a flashlight beam at another flashlight beam, and it doesn't emerge from the second one. A beam of light can actually absorb another beam of light. Another problem with gamma rays is that they can be produced by other processes other than from hadronic cosmic ray interactions. So we turn to our third messenger, which is neutrinos. Neutrinos we know are produced from basic particle physics. We know that they're produced in hadronic cosmic ray sources, and we don't have this problem that they could be produced by other processes. So if we identify a neutrino from a source, it must be a source of cosmic rays. Okay, how does this work? So what are the signals and backgrounds in neutrino astronomy? Here's a diagram of that same cosmic ray proton that I showed earlier. When it collides with the atmosphere here on Earth, it initiates this cascade of interactions, basically by splintering a molecule of air and then continuing multiple steps of particle physics interactions. The main particles that survive to ground level and even below ground level are muons and neutrinos. Muons are sort of like a heavy cousin of an electron. Neutrinos are very low mass, chargeless particles which can travel large distances through matter. They almost don't interact with matter. So we're interested in detecting both muons and neutrinos. The challenge of astronomy is that of neutrino astronomy is that we have large backgrounds that we need to identify neutrinos within and then identify astrophysical neutrinos within them. So one of the most powerful techniques we have for doing that is using the energy of the individual particles that we detect. So here's a diagram with flux of particles on the vertical axis, energy on the horizontal axis, and you can see this spectrum of what we call atmospheric neutrinos. These are these neutrinos produced by cosmic rays hitting the atmosphere. It's a very steeply falling energy spectrum, and so we're looking for an excess of additional neutrinos on top of that steeply falling energy spectrum. And that's kind of a signature of astrophysical neutrino signal on top of the background. So we're looking for a haystack, for a needle inside a haystack inside a haystack. So we have these atmospheric muons which are traveling through the ice at the detector continuously. IceCube detects 70 billion of those per year. Within that haystack, we're looking for atmospheric neutrinos. That's closer to what we're looking for, astrophysical neutrinos. That's 1 in 1,000 of those muons. But they're still coming from the atmosphere. They're not coming from the astrophysical sources that we're interested in. Now that, compared to that original 70 billion, only 1 in 10 to the 8 of those particle events are the astrophysical neutrinos that we're interested in. And there's also this challenge that neutrinos are very unlikely to interact in matter. So we need a huge detector. Okay, so a little bit of history. You can start the history of neutrino astronomy in various places. I'm going to start where Wisconsin became a leader in the field, and that's with the publication of this paper in 1991. So there was a simple experiment. A group of people, including 2 from the University of Wisconsin, Francis Halzen and Bob Morris, installed 3 simple photomultiplier tubes, like the one you see in front of you, inside a hole in Greenland, and they detected these atmospheric muons for the first time in ice using a Cherenkov detector. So Cherenkov radiation is produced when energetic charged particles travel through a transparent medium. They make a flash of light as long as they're traveling fast enough. And so that's the basic technique that we use. So they knew, based on the simple detection of atmospheric muons, that they could detect atmospheric neutrinos, which convert into muons, and then from there detect astrophysical neutrinos, back in 1991. The next milestone was to build a bigger detector now at the South Pole rather than in Greenland. This was called the Amandla Detector, again with leadership from the University of Wisconsin, support from National Science Foundation, also Department of Energy, and of course the Wisconsin Alumni Research Foundation played a key role in supporting Amanda. And now Amanda made an interesting milestone. It detected not just atmospheric muons, but also atmospheric neutrinos for the first time. Whereas atmospheric muons travel downward through the detector, they cannot travel through the entire Earth. Atmospheric neutrinos can travel through the entire Earth. So if you see an upward going signal in your detector, you know that it must be a neutrino rather than a muon. Okay, so that brings us to IceCube. Based on the success of Amanda detecting atmospheric neutrinos, a much larger detector was proposed and built. Amanda was the predecessor of IceCube. And so here you can see the IceCube detector. I've already explained the basics of it, so I'm going to keep going. It's basically a large array of these simple sensors. And it was commissioned in 2011. And so here's the basic idea of how it was constructed. It's a really simple idea. You squirt hot water at high temperature and high pressure. And you just keep squirting that until you drill a hole, which is 1.5 miles deep. Simple idea, but a huge engineering challenge in this harsh environment. It was made possible thanks to leadership by the Physical Sciences Lab here at the University of Wisconsin. So IceCube is led by a large collaboration of scientists from around the world. Here you can see the member countries. It's a great team that has made the results possible that you'll hear about today. Okay, what are the different neutrino types and how do they interact? There are actually three different, we call them flavors, different types of neutrinos. So here's a muon neutrino. It's called that because a muon neutrino converts into a muon, which we can detect with this long straight track. There are also depositions that we call cascades or showers. For example, from an electron neutrino, which just makes a spherical compact deposition. And then there's another type called tau neutrino. We don't yet have strong evidence that we've detected these, but we have detected the first two. Okay, so as soon as we turned on the detector and took the first couple years of data, we discovered some really interesting events. And so they look like this. Here's the cascade type shape that I showed you before. It's very high energy, hundreds of times more energetic than the particles produced at the Large Hadron Collider. Here's what this looks like for scale if you're familiar with the Mendota Lakeshore. It's almost as large as the entire UW campus. So here's the union in the red gem. You can see enormous amount of energy deposited by this neutrino. So the big mystery after we've discovered the signal is, of course, what's producing them. And so the obvious thing you do is you make a map. This is neutrino astronomy, after all. You make a map of where all these events are coming from. Now, this map includes astrophysical neutrinos. It also includes atmospheric neutrinos and atmospheric muons. And when we make this map, we don't see any clustering from any particular direction on the sky. So far, we have not found any individual sources of astrophysical neutrinos, even though they exist because we detect a diffuse emission of astrophysical neutrinos. So the next step that we did is we tried to do all this much faster. So the first analyses took a year or more to do a very sophisticated analysis and to identify the signal. And then we realized that we want to do multi-messenger astronomy with partners in real time. So can we do this in a minute rather than in years? And we succeeded in doing that. So when a neutrino collides with the ice, makes a flash of light, we detect that, we determine it's interesting, it might be an astrophysical neutrino, we relay that to satellites back down to the ground to partner telescopes around the world. We do all of that within a minute. And that lets all of our partner observatories point in that direction and see if they also see an interesting signal from that direction. That'll be a key part of the story that we'll hear today. So that's the quick overview of the IceCube Neutrino Observatory. Of course, we have very low statistics of these astrophysical neutrinos, on the order of 10 per year. And so we need more. So we have plans to build a much larger detector, increase it by about an order of magnitude, and increase our rate of astrophysical neutrinos by about an order of magnitude. And now I'll hand it over to Jay.
Thanks, Justin. Okay, we can do, I'll just use this one.
That's the clicker if you want it.
Good morning. So let me continue along here and provide a little bit of the astrophysical background for you. Can you hear me without the mic? I don't know if it's on. Mic's not on. There we go. Now it's on. Is there any difference? There it is. Yeah. Okay, good. Took a second. All right. So let's look a little bit at what the astrophysical implications are of multi-messenger astronomy and why are we doing it. So the first point to make, which comes here, is that there is a large, whoops, that didn't work. Whoa. What happened again? There it is. There is a large, I'm going to deal with this. This seems to be part of the problem. There's a large energy difference between, let's see if I can get this to work, pointer. There it is. Okay. There's a large energy difference between the energy of the neutrino that you find here and the energy of cosmic rays over here. And so what you need to produce high energy neutrinos is you need some kind of a cosmic accelerator that produces energies that are thousands of times larger than the energies involved in nuclear reactions. In other words, there are two classes of astrophysical neutrinos, those which come from fusion and associated processes, but this is something else. This is where Mother Nature plays with particle physics. So the question is, what kind of an environment can produce the energy densities that we need to make these very high energy particles that in turn yield neutrinos that we see? And why can't we solve this problem in some other way? After all, cosmic rays have been known to be impacting on the Earth. We detected them more than 100 years ago. So what we need to carry this off is we need a cosmic accelerator of some type. We need some kind of a power source. In astrophysics, there's really, in very high energy density environments, the main energy sources are gravity. When you compress things together around a black hole, you get gigantic energy densities. So that's one potential power source. Another power source are supernovae, which combine fusion, basically a natural bomb exploding, and again gravity as the core of the star collapses. So these are two ways that you can produce very large densities of energy that we need to potentially accelerate particles. Now, you also have to couple to the particles somehow. And this is done by magnetic fields, which we see on the sun, because the magnetic fields confine the particles and a lot of the energetic protons and atom nuclei, and these allow then the atoms and nuclei to be accelerated. And the process involves shock waves or cosmic blast waves. So we need a combination of a magnetic material, we need matter moving rapidly, and we need large energy. This is enough to produce very energetic particles up to relativistic velocities and the kinds of energies above the LHC. This is a process that was understood, for example, by Fermi almost a half century ago, more than a half century ago. To get neutrinos, then, we need one more step. Neutrinos come, as Justin explained, from interactions between particles and another particle, light or atoms. So we need a target. And the target can either be gas or photons. And these targets then produce the neutrinos. This means we can actually see into sources where the particles don't get out, where they're being absorbed by these interactions. So we have a range of possible environments. Now, energetic processes produce also very energetic photons. The most energetic photons are gamma rays, and as Justin explained, gamma rays also come to us from distant sources. The problem is that you can get gamma rays out of two classes of sources. A powerful source can have electrons and positrons in it and make gamma rays, but it will not make cosmic rays. Another source, but adding protons or hadrons into it, will produce cosmic rays, but as we discussed, the cosmic rays do not come directly to us, they're deflected by the magnetic fields. So the only way we can tell the difference between these two sources in a direct manner is to detect the cosmic neutrinos. So the cosmic neutrinos are a way to find where the accelerators are that nature is using to make the most energetic cosmic rays, with energies well above that which we can produce here on Earth. IceCube's goals, one includes understanding the physics of these processes and also detecting these kinds of systems, which are unknown up till now. So what are the possibilities? One possibility is an exploding star. Exploding star, there's a thermonuclear explosion, and the core of the star suddenly drops in size from something Earth-sized to something the size of Madison. And this disrupts the star and produces a blast wave of materials traveling out at 10,000 kilometers a second. In some extreme cases, shown over here on the right, the star will actually produce a jet of energy coming out, a gamma ray jet, and this gamma ray jet will accelerate particles to even higher energies. These high energy jets are seen in gamma rays as bursts, and that's shown over here. And this is in seconds. From here to here is 100 seconds. So in 100 seconds, huge amounts of energy are deposited as the star disrupts. This is an environment that potentially could accelerate cosmic rays. And thus, we look for them. The target could be surrounding material or light associated with the eruption. So here's a possible stellar source. Another possible stellar source, which has become much more feasible thanks to multi-messenger astronomy, is nature sometimes makes stars in binary stars. In fact, we always say in the elementary astronomy class that 3 out of every 2 stars is in a binary. Most stars have companions. The sun is sort of second class. We do not have a stellar companion. Massive stars in particular are very prone to having stellar companions. This companionship, though, as you know, all relationships that are binary are a little unstable sometimes. And in this case, the neutron stars, due to a relativistic effect, can actually merge together. You have 2 solar mass objects the size of Lake Mendota. When one of them gets to be a sort of Lake Kagansa, you're in trouble. The 2 stars will merge together, They'll radiate a huge amount of energy in gravitational waves, which we detect, and potentially also produce light and particles at very high energies. Now notice that both of these classes of stellar sources are transients. These things occur on timescales of seconds. So these are bursts of energy on timescales of seconds that could inject high energy cosmic rays, and we know inject gamma rays into the universe at huge luminosities. Now, another possibility is a galaxy is nothing more than a bunch of stars together. Here is the galaxy M51, an image taken by Alison Noble for her undergraduate thesis here with the 1.9 meter telescope. And here is a blow-up of it with the Hubble Space Telescope. This one costs almost nothing to run. This one costs a fortune to run. And you get a better image out of it, too. So what you see there, all those blue dots are stars. So there are many, many potential stellar sources in star-forming galaxies, and perhaps these combined are our major source of cosmic rays. However, we have not detected very many of these galaxies, even in gamma rays yet. What we have seen are galaxies like this. This object here is a disk of stars, and the material you see sticking out is a cosmic blast wave traveling at a velocity of more than 1,000 kilometers a second. In this tiny galaxy, a region, this center part, by the way, is about the same as the distance between us and the Orion Nebula. In that region, there are more stars being formed than in our entire galaxy. So this huge region is called a starburst. And in a starburst, the supernovae interact, the energy densities get higher. So of the star-forming galaxies, the most likely candidate to produce observable neutrinos and cosmic rays are these very high star formation rate systems. Here is an image with the Fermi telescope of this galaxy showing it's detected in hard gamma rays. So galaxies are a possibility, and starbursts are a good bet. Now for neutrinos, they're also good bets because they have a lot of dense gas that supports the star formation. Dense gas is the fuel for stars. It makes great targets. So these are potentially a place where you can accelerate lots of particles, have them interact, and get the signature of it from the neutrinos. Now, another possibility are active galactic nuclei. The centers of most large galaxies contain supermassive black holes, millions to billions of solar masses in regions the size of the solar system. These are nature's most compact, highest energy density regions. So this is where you can get huge energies. And what happens is that as material is accreted onto the black hole, it releases gravitational energy, and huge amounts of power come out. The power that's generated can be hundreds, thousands, or even tens of thousands times that of all the stars in the Milky Way. And it's concentrated in a tiny volume. This in turn leads to jets of relativistic particles coming out, which emit light. And this light is a signature of the process that's going on. Now the problem is we don't know what's in these jets. However, it's a big difference whether you're looking at the jet from the side or head on. Think of a highway at night. It's a dark night. You're out in northern Wisconsin. You can see that it's a truck coming by its faint shadow. You see the headlight shining ahead. Okay, now you're a deer in the highway. All that you see is a bright light coming at you. You can't tell if it's a truck, a motorcycle, or even something stationary at the end of the road. That's the situation with these AGN. If you look down the jet, you get a very, very bright source. And this leads then to a class of object called blazars. Just like the starbursts are the most extreme examples of star-forming galaxies, blazars are when you look down the jet and you see a very, very bright source. There are two classes of blazars, BL-lac objects, where we only can measure the jet, and flat spectrum radio quasars, where you can see a little bit of the surroundings. But this is a case where you look down the jet. But the problem is we don't know, is this jet full of only electrons and positrons, or does it have protons in it as well? Is this the cosmic accelerator? Okay, and that's the astrophysical introduction, and we're about ready now to go to the NSF's conference. Thanks.
So while Ellie's setting it up, just a little bit about the plan. So the press conference should run about an hour, and we'll stay connected for the first few minutes of questions at that press conference, and then we'll cut that off and take questions here. So if you have specific questions for me and Jay, we can take those. if you're interested in watching the rest of the questions or more of the press conference, that will be archived at NSF, so you can watch the rest of it later.
And alternatively, you can submit your questions to symposium@nsf.gov. In addition, we have reserved room 2010, which is located down this main hall back here, for interviews following the formal remarks. This event is being recorded and will also appear on NSF YouTube following the event. You can join the conversation on social media using the hashtag #BlazarNeutrino, and you are invited to join an online AMA on Reddit, hosted by our partners at the University of Wisconsin, beginning after the press conference. With that, I would now like to hand it over to Dr. France Cordova, Director of the National Science Foundation. Please join me in welcoming Dr. Cordova.
Thank you, Amanda, and good morning, everyone. Welcome to the National Science Foundation, the place where discoveries begin. In 1912, physicist Victor Hess had a problem. He was trying to find the source of a particular kind of ionizing radiation that he believed came from space, but he was just too close to the ground. So Hess did what scientists and engineers have done throughout history. He devised a way to collect the information that he needed. Accompanied by what must have been some very patient friends, he began 2 years' worth of balloon ascents, taking electroscope measurements far above the ground. Just 9 years after the Wright brothers' first flight, in a small basket 5,000 meters in the air during a near total solar eclipse, Victor Hess found the first evidence of cosmic rays. For this discovery, he was awarded the Nobel Prize. As so often happens in science, Hess's findings raised new questions, opening the door to a mystery that has endured for more than a century. What are the origins of high-energy cosmic rays? In 2004, a group of researchers, supported by the National Science Foundation, also had a problem. They wanted to track high-energy neutrinos, elusive subatomic particles that travel the universe at almost the speed of light. High-energy neutrinos are incredibly hard to study. They have no electrical charge and are almost weightless, penetrating matter as they whiz across the cosmos. We can only see evidence of them when one happens to crash into the nucleus of an atom. If you had a detector the size of your body, you might register a collision between a high-energy neutrino and a nucleus in your body only once every 100,000 years. So like Hess, these researchers devised a clever solution. They created a cutting-edge laboratory in Antarctica, one of the harshest environments on the planet, and also the only place suited to this task. They constructed, with NSF funding, the Ice Cube Neutrino Observatory, which sits above a cubic kilometer of crystal clear ice that is permeated with over 80 long strings of sensitive equipment, a massive engineering undertaking. You can think of these strings like strings of pearls in which every pearl is a digital optical monitor, like the one on this stage. And there are over 5,000 of them in this cubic kilometer of ice. Today, I'm proud to announce that using data gathered by NSF's IceCube, an international coalition of scientists has taken a major step towards solving the high-energy cosmic ray mystery, echoing Hess's spirit of innovation. They believe they may have identified at least one source, another galaxy billions of light years away with an especially active nucleus known as a blazar. Blazars are powered by supermassive black holes and spew immense jets of mass and energy that can be the size of a visible galaxy. These jets accelerate cosmic rays and contain particle collisions that result in high-energy neutrinos. And as in all blazars, one of those jets points directly at us. This discovery will enhance our understanding about how the universe is built and behaves. We will better understand the nature of the universe's immense cosmic accelerators, which are far larger and more powerful than anything we could build on Earth. Despite all the progress we've made with particle accelerators, like the giant ones at CERN and Fermilab, we still can't produce anything with nearly the energy of these cosmic particles. So we have to turn to the heavens to deepen our understanding of the highest energy processes. Creating NSF's IceCube was a difficult process, but the rewards have justified the investment and again demonstrate the importance of building entire ecosystems of basic research. This work would not be possible without the foundational discoveries made by neutrino physics pioneers, including Nobel laureates Melvin Schwartz, Frederick Reines, and Raymond Davis, all NSF supported. Discoveries like this build on advances that result from years of painstaking investigation. The federal government has a unique role in these discoveries as the only supporter with the resources and mission to ensure that high-risk, high-reward, long-term research continues. Like the recent detections of gravitational waves by the NSF-funded LIGO facilities, this work shows that consistent investment in basic research pays off. This result is the first of its kind. We have never before used multi-messenger astrophysics to pinpoint the origins of high-energy cosmic rays. I want to commend the researchers for how they've presented this to the world. The experimenters take care to quantify the statistical significance of the spatial and temporal coincidence of the high-energy neutrino detected by IceCube and a blazar flaring in gamma rays. Like Hess's discovery of cosmic rays, these first results will raise new questions and open doors for new research. As in all good science, this is only the beginning, and that's exciting. Now, let's hear about the new updates from today's presenters. I'd like to welcome Frances Halsen, Principal Investigator of the IceCube Observatory at the South Pole, Regina Caputo, Research Astrophysicist at NASA's Goddard Space Flight Center in Maryland, Razmik Mirzoyan, Senior Astrophysicist at the Max Planck Institute for Physics in Munich, Germany, and Olga Ottner, Professor of Experimental Particle Physics at Uppsala University in Sweden. First, Dr. Halsen.
After the director's introduction, I think I should show a picture of Victor Hess, who just ascended to 17,000 feet without oxygen. He discovered cosmic rays, which are not rays, they are nuclei, mostly protons. And we don't know where they come from. We have been seeing neutrinos since 2013, and we still didn't know where they came from. It's one of the oldest open questions in astronomy, and of course the issue fascinates particle physicists because cosmic ray accelerators routinely accelerate particles to 10 million times the energy of the Large Hadron Collider beam in Geneva. So to track cosmic accelerators, that was actually always meant to be the flagship mission of IceCube. We transformed a kilometer cube of ice a mile deep under the geographic South Pole, under the Amundsen Scott National Science Foundation station, into a neutrino detector. And it's very simple. You fill a kilometer cube of ice with 5,160 light sensors and you detect neutrinos. So this is a neutrino, an optical module, an optical sensor, starting a trip probably 2,400 meters deep, and that's the last time you see it. So why neutrinos? This is like a theorist image of a cosmic accelerator, a black hole of some kind, and it managed to transform some of its gravitational energy into accelerating particles. So there are accelerated protons because it's a cosmic ray source, and they will interact with the light in the galaxy and with the hydrogen and produce neutrinos. So the goal is to track cosmic ray sources by looking for neutrinos. And so they will point back, they're neutral particles, they will point back at the source. And on September 22 of last year, that's exactly what one neutrino did. And you can see it coming through the ice, lighting up the sensors. In fact, you don't see neutrinos. What you see here is a muon, which is a particle that was made by a neutrino somewhere to the right of the detector, and that streaks at the speed of light through the ice, lighting up the sensors by the blue light that it emits. So within 43 seconds, the computers at the South Pole captured these signals, reconstructed the energy and the direction of the track, and sent it for any telescope in the world that would be interested in it. This is the event. And so what we found out is that sometime later, if you look at the picture on the left, within 0.06 degrees, Fermi was aware of a source, an active galaxy, that actually was flaring. It had, in the last few months, increased its output, its power, by a factor of more than 6. Subsequently, the MAGIC telescope that detects the highest energy form of gamma rays that we detect in astronomy detected that the source emit TV gamma rays. This is a very unlikely event. So by then this was interesting, and more than 20 telescopes, which are shown on this slide, looked at the direction of this event. So that's, however, only the beginning, because now we knew of an interesting place in the sky, both Fermi-LAT collaboration and the IceCube collaboration. We have stored some 10 years of data on tapes and now disk. And we can go look back in this direction, and that's what we did. And while the event I'm talking about was dominated by essentially one 290 TeV neutrino, when we look back in our data, we found that in 2014 there was a flare in neutrinos, more than 12, that came in 150 days. When we measured the energy distribution, the energy pattern of the neutrinos, is exactly that what we expect from cosmic accelerators. In fact, that's the same is true for the gamma rays in 2017 and 2014. So what did we discover? Well, we discovered one source of cosmic rays. It's a supermassive black hole. that powers the accelerator and produces the neutrinos and the gamma rays subsequently detected. This is only the beginning, but through this campaign we have collected an incredible amount of data on this source, and most important, we know it accelerates protons and not just electrons. So this is actually not the first time multi-messenger neutrino event occurred. It occurred in 1987 when a supernova exploded in our local neighborhood. But who could have guessed that we would stand here 30 years later and report a similar event with neutrinos that are 10 million times higher energy from a source that's 100,000 times further away in the universe. So to tell you the rest of this story, I'd like to introduce Regina Caputo, who is the analysis coordinator of the Fermi Lab collaboration.
Thank you, Francis. It's a privilege to be here today speaking on behalf of the Fermi Large Area Telescope collaboration, a collaboration of over 400 scientists from around the world who are constantly monitoring the gamma ray sky. So the object that we're talking about today, as you've heard a few times already, is a galaxy. And this particular galaxy has a very dense core at the center. And at that core is a supermassive black hole that's millions to billions of times of the mass of the sun. Now, it's surrounded by gas. And what you're looking at in this visualization is this central core of a galaxy. As we go in, you'll see this gas that gets gravitationally compressed into a disk and gets accelerated and swirled around this central black hole. Now, sometimes these particular galaxies shoot out jets of particles. These Blazar Jets are true cosmic accelerators, and they accelerate particles to the highest energies, higher than we can see on Earth. Now, when that jet is pointed at us, that's what we call a blazar. Now, the Fermi Large Area Telescope, or the LAT, observes the full sky. And the scientists who analyze Fermi data are constantly checking for objects' variability and changes in that gamma ray sky. And so what you're looking at here is an image of the northern hemisphere of the galaxy in gamma ray data. And you'll see a time-lapse image over about 8 months of these flaring objects. So you see they change, the flux changes and flares and increases. And what are circled are the 11 most energetic blazars that we observe. We actually observe over 2,000 blazars in the gamma ray sky. So this particular blazar, called TXS 0506, is located in the Orion constellation, but it's about 4 billion light years from Earth. Now, if you are looking at the sky at Orion, this is about what you would see with your eyes. But the way that we see it in gamma rays, and we'll go ahead and outline Orion as a reference, you see it's the source right there under Orion's arm. Now, this particular source is a bright Fermi source. We've seen it for 10 years. And starting in April, it experienced one of the largest flares that we had, well, the largest flare that we had ever seen from this particular source. Now, Fermi is on orbit in space, which is probably the only place that's more inhabitable than the South Pole. And what you see is gamma rays coming in the magenta squiggles, formed in the same place as the Blazar jet with the neutrinos. And Fermi detects gamma rays, as you can see illustrated when it lights up in magenta, although it doesn't actually do that. And the neutrinos sometimes pass straight through the Earth. Now, just to give you an idea of what this source looked like for the first 10 years, we have a time-lapse video showing the gamma ray data as represented by these circles, where the size and color of the circle is representative of the energy of the gamma ray that entered. And so you could see, we see lots of gamma rays from this source. It's an active source, it's bright. And this is what a typical emission state looked like. Then, because we're able to monitor the sky all the time, we were able to notice that during April, which starts right now, that the number of gamma rays from this source increased by a factor of more than 6. So it was very, very crazy emission from this source. And I stopped it on September 22nd, 2017. And you'll see just how bright this source was in gamma rays as represented by these circles. And so it was really, really exciting when we got the notification from IceCube, because as I've mentioned, Blazar's flare, but the fact that we could tie together the gamma rays and the neutrinos tells us something very exciting about the particle jet and the particles that are being accelerated. So we've now entered a new era, starting last year with the joint discovery of gravitational waves with gamma rays from Fermi. We were able to view a cosmic explosion when 2 neutron stars merged, and we were able to detect it in these multi-messengers. Today we're really excited to report, now we know something about cosmic accelerators in the joint detection of neutrinos and gamma rays. And so to give you more information about the 20 observatories that followed up this very exciting notification, I'd like to introduce Dr. Razmik Mirzoyan from the MAGIC collaboration, who's the MAGIC spokesperson. Thank you.
Good morning, ladies and gentlemen. I feel privileged to be today here and to talk from the name of the MAGIC collaboration and to talk about measurements done by MAGIC in this big event, in this multi-messenger detections. In astronomy, we are observing objects at different wavelengths. You can see, just as an example here, I show you SEN-A, the source observed in X-rays or in optical wavelengths, in the radio continuum, and then you can see that the source is looking very different depending on at which wavelength it is observed. And then this multitude contains a lot of information which allows us to understand the source nature. But now imagine there is a multi-messenger detection, and neutrino is coming into the game. And I should tell that I can remember something like 25, 30 years ago, many discussions with my colleagues, with my friends, and they were saying sometime in future, maybe it will become possible to measure sources not only across the electromagnetic spectrum, but also maybe one can measure with ground-based instruments neutrinos. And I'm very happy because today it's becoming reality. On 22nd of September 2017, IceCube set an alert for an extremely high energy neutrino, and a few days later, Fermi collaboration measured a signal from a particular direction, practically coinciding with the direction indicated by IceCube from an object with the name TXS 0.0506, and then that was followed with other measurements, MAGIC telescopes measured on during 12 hours a strong signal from the same direction like Fermi has indicated, and this was followed by an avalanche of other detectors, almost 2 dozens of instruments across the electromagnetic spectrum worldwide measured signals. So this is the MAGIC collaboration. It's a middle-sized collaboration consisting of about 175 astrophysicists, and 2 weeks ago we were celebrating 15 years of anniversary of operating our instrument on the Canary Island of La Palma. So these are the 2 MAGIC telescopes which are located on the Canary Island of La Palma at an altitude of 2,200 meters above sea level. And this is very different from what Regina has described and Francis has described. We have nothing to do with the ice in the South Pole or high up satellite mission. I think this is La Palma is well known as a resort place, a place for doing vacations. So we are enjoying having vacations and doing science together, and we try to do it very efficiently. These two telescopes, they have a 17-meter diameter each. They have a focal length of 17 meter, and they are separated on 85-meter distance from each other. And these are really high-tech telescopes. They introduced a lot of new techniques and methods into the field. One of the distinguishing features of these telescopes is we can rotate them very fast. Within 20 seconds, we can go to any direction in the sky, and this is very crucial when a fast alert is coming, like the one from IceCube. So in this cartoon, I would like to give you an impression what we are measuring with these telescopes, because the telescopes are somewhat different from usual optical astronomy. Our Earth's atmosphere is not transparent to gamma rays. They will be absorbed very fast. Somewhere on 25 kilometer height, gamma rays get absorbed. But then they produce secondary particles. And the secondary particles, mostly electrons and positrons, they move with a speed higher than the speed of light in the air, and they emit this bluish light, this blue color light. So these telescopes are measuring this, collecting this blue light, and then focusing it into the focal plane, where an imaging camera will measure the shape of an air shower in the atmosphere. And then based on this shape, we can measure the energy and then most parameters of these gamma rays. This is how these telescopes are working. Here I would like to show to your attention a cartoon. This cartoon is about an attempt to understand how these multi-messenger detections happened in total, to have a big picture. So for understanding this picture, I would like to tell you that today there will be published 7 papers devoted to this event, and I'm expecting that an avalanche of papers will follow in the next times. But from these 7 papers, 2 will be published in the Science magazine. There are 5 more papers. So this is an attempt of an accompanying paper from a magic collaboration, where we try to talk about Blazar. You see the jets of the Blazar, and then you can see zoomed in jet, and then under special conditions, I think you can have relatively low energy photons, and these photons can interact with electrons, and then due to this interaction, so-called via inverse contact mechanism, you can get gamma rays, but also protons are there, and these protons can interact with these photons, and then they can create via photomeson production, they can create pions, which will later on decay to neutrons. So you look to the picture, you see the red color as the protons, and because of the charge, they move in a zigzag line, so they deflect in the different magnetic fields. So when we measure protons, we cannot say the incoming direction, but you pay attention to the green line. These are neutrinos, which are detected by IceCube at the South Pole, and you pay attention to the blue lines. These are measured by Fermi satellite and then magic telescopes. These are gamma rays. So I think we tried to get a consistent picture, and in this picture I think we can explain very well how it comes that we can measure simultaneously neutrinos and gamma rays in different energy ranges. And then when you measure neutrino is a smoking gun for a parent proton. So if you measure about 300 TeV neutrino, it means that there is at least order of magnitude high energy proton. So these protons are in the jets of blazars, and this seems to be the first time that we can say something serious about the long-standing question where the protons are accelerated, and protons are nothing else other than cosmic rays. So it means that blazars can contribute cosmic rays at extremely high energies. This is a very strong message. And with this message, I would like to give the word to my colleague, to Olga Botner, former spokesperson of IceCube collaboration. And she is going to present details of the accompanying paper of IceCube collaboration, second paper in the Science magazine. Thank you very much for your attention.
So it's a great pleasure for me to stand here in front of you on behalf of the IceCube collaboration. 300 scientists from 12 countries around the world on 4 continents. And most of them young and not gray-haired like Francis and myself. 300 sounds like a lot, but the number underscores the tremendous effort which has kept the dream of neutrino astronomy alive for the past 3 decades. From the tentative beginnings around 1990 to the proof of concept with the Amandla prototype array at the South Pole in 2001, to the breakthrough discovery of highly energetic cosmic neutrinos with IceCube in 2013, to today's exciting news, the first evidence for a source of such neutrinos. As you've heard several times today already, IceCube's September 2017 alert, in association with gamma-ray observations, pinpointed an astrophysical object named TXS-0506 and sometimes nicknamed the Texas source as the most likely source of these neutrinos. And what you are looking at on your right-hand side is a picture of the sky at radio frequencies at the position of the blazar. And you are, as it were, looking directly along the barrel of one of the Blazar Jets. That's the bright white spot at the center of the red blob. Now, intrigued by this association, we decided to look in our archival data to see if we could identify any more neutrinos coming at us from the position of this source. As you may know, IceCube was completed in 2010, but we had been taking data in partial configurations already for several years before that date, and so we had about 10 years of data to scrutinize. And, amazingly, we discovered a neutrino flare centered on December 2014. During a period of 5 months, we observed 19 events where we expected about 6 events from cosmic ray interactions in the atmosphere. This is an additional bit of evidence indicating that the blazar is indeed a source of high-energy neutrinos. What I'd like to do now is to play a movie for you, a movie showing how the neutrino signal accumulates over the 5 months. So here goes. From nothing to a peak and disappearing again. And on your right-hand side, you see a timeline with the neutrino intensity as a curve and the arrow indicating the time interval of this movie. I want to just show you the intensity at the peak of the flare again. So this white spot, the bright spot in the center of this sky map at the position of the TXS is the neutrino flare. So as I've just told you, we detected 13 neutrinos, which we believe are signal from the direction of the Texas source in the 2014-15 flare. During these 5 months, 15 million neutrinos at similar energies and from the same direction passed IceCube unseen. And this ratio 13 to 15 million illustrates very well how hard it is to catch a neutrino. A neutrino is invisible unless it collides with an atom, and this happens very rarely. And so you need to monitor a tremendous lot of atoms to stand a chance to catch a neutrino. IceCube at NSF's Amundsen Scott South Pole Station instruments a volume of 1 cubic kilometer of the clearest glacier ice. This is 1 billion of tons of ice, 10 to the power 38 atoms. This is a 1 followed by 38 zeros. On your left-hand side, you see how the IceCube sensors, like the one which is standing in front of you on the podium, are attached to cables, deployed into vertical holes drilled by means of hot water, and left to freeze in the ice. On your right-hand side, you see a neutrino coming from the bottom right, colliding with an atom, producing a charged particle which is called the muon, which then moves through the entire depth of the detector, trailing a cone of bluish light. And it's this light that our sensors detect. Now, the colors you see in this picture are not the colors of the light, but they illustrate the time sequence of the signals we observed, with the reds and oranges being early and the greens and blues late. So as you can see for yourselves, from the time sequence, we can reconstruct the direction of the muon and hence the direction of the neutrinos. So this is how we know that the neutrinos we observe come from the TXS source. In 2013, IceCube made a breakthrough discovery of a diffuse flux of highly energetic astrophysical neutrinos. Since then, we have observed a couple of hundred such events. And what you see in the upper panels on this slide are the 4 highest energy neutrino events ever observed on Earth. What you are seeing is not the neutrinos themselves, but the light images as they are recorded by IceCube. And to give you some kind of feeling for the dimension, think in terms of hundreds of meters and kilometers. On the picture below, you see the directions of these high-energy neutrinos distributed over the sky. And as you can see for yourselves, there is no obvious accumulation of directions. So the million-dollar question has since then been, where do these neutrinos come from? And for the neutrinos we're reporting on today, we know the answer. We needed electromagnetic observations to assess the association of the September 2017 alert with an astrophysical object. The neutrino burst in 2014-15 strengthens this association. And so the bits of the puzzle are starting to fall into place. For the first time, we have been able to associate high-energy neutrino emission with a high-energy gamma-ray source. This is what we've been waiting for. This is the first evidence for high-energy cosmic accelerator, a pivotal moment for multi-messenger astronomy. Now, as you see in this graph, on your left-hand side in the bottom corner, I show also the gravitational waves. And as most of you know, we have not identified neutrinos in connection with gravitational wave events yet. But we believe that this is the discovery waiting for us just around the corner. Thank you.
Well, there you have it. So now we're open for questions.
Hi, this is Emily Conover from Science News. I wonder if you could talk, you've got one neutrino now that's associated with this Blazar. What's sort of the future of this kind of work? How soon can we expect another one? I mean, obviously that's hard to predict. But, are there any plans for future upgrades that might increase the rate, things like that?
Okay, well, first I'll have Olga just clarify that there's actually more than one, and then ask Francis to address your question.
Yeah. So just to make it quite clear, there is 2 papers published in Science. One is the paper about the 2017 alert, and this is one high-energy neutrino pointing at the spot in the sky. But then in our archival data, we have more than a dozen neutrinos coming at us from the same direction. So we have actually a handful of neutrinos from this object. And this is why we are confident that this is a source of neutrinos and a probable accelerator of high-energy cosmic rays. Now, about what we would wish for the future, this is, of course, a good question. And I've tried to explain that neutrinos are very, very difficult to catch. So, to get more, you need a bigger detector. And I let Francis continue.
Well, the short, direct answer to your question is you saw it actually on one of Olga's plots. In the last 9.5 years, we saw 2 bursts. And that's the only information we have right now to predict when we'll see the next one. The key, I think, is this source is very special because, you know, why do we detect the first source 10 times further away where there are very nearby sources? And so the key is to find other sources that do this. And then hopefully you can beat this 2 times in 10 years time scale. But as usual, the work has just begun.
Francis, are there plans, just following on that question, are there plans to make the IceCube observatory bigger?
Of course.
That's the answer she wants.
And I'll just add to that, you also want to keep continuing to monitor other high-energy particles like gamma rays to have these joint detections. Because that's, so you want to continue to monitor the gamma ray sky as well.
Great. And once LIGO is up and running again, right now it's being refurbished to have higher sensitivity, which is really important in these things, then we can see, as Olga said, the last piece of that puzzle falling into place in multi-messenger astronomy. Another question, please.
We have a follow-up. Sorry, I just wanted to ask about the when you look back in the data and you see the neutrinos, you know, this handful of neutrinos. Is there any evidence of a gamma ray flare at the same time or anything like that?
So there's 2 things you basically have to look for: the number of gamma rays and the energy of the gamma rays. And so at the time of the neutrino flare, we didn't see an increased number of gamma rays, but there is some evidence to indicate that we saw an increased energy in the gamma rays, because they're produced at the same time. The same process that produces neutrinos also produces gamma rays. That's why the energy is also important. So we didn't see an increase in the flux, which is why, and we didn't have an alert from IceCube, but you know, also Fermi, all of the data is archived, so we can go back and look at the data and see what was happening at the same time.
May I just add
yes,
a sentence? I mean, this is actually very exciting, right? It's not clear-cut science. We are learning about the blazars as we go. They don't, you know, it's not as it was predicted. It's not as we had expected. There's more things going on, and we are learning new things. So this is just the beginning. Just
the physics of jets, just so you don't think that that's all been figured out, is really has a lot of mysteries in it. And this is another piece, as Olga's just said, of the puzzle of how do particles get accelerated to these tremendously high energies in these kinds of environments. And as I said in my opening remarks, this is so much higher energy than what we can produce on Earth in our best accelerators. Another question.
Yeah, hi. Arthur Friedman, the UCO reporter. So I'm wondering, are the neutrinos traveling at the speed of light? And other part of the question is, if they were in a gravitational wave, would the gravitational wave accelerate them even faster, or are they already at the maximum speed? I was just trying to understand the interaction if they were a part of a gravitational wave but undetected so far.
Francis?
No, I mean, when we say they travel at the speed of light, of course, it was a major discovery in '98 that neutrinos actually have a small mass. But this mass is so small compared to the energies IceCube is observing, it's totally irrelevant. So neutrinos are basically like photons. And so there's no difference. I don't know if this answers your question. I'll give you an example of an event where we would see neutrinos and gravitational waves. And we are all waiting for it, as I said. 30 years ago, an explosion and a collapse of a star, unless it were perfectly symmetric, would produce gravitational waves. and we know that we can see neutrinos. So that's one case. The neutron star merger, which is still on the screen, actually make jets. When they spiral in, a jet is formed, which is very similar actually in concept to what we are talking about here. And presumably this source emits neutrinos in some similar mechanism than the blazars. And of course, the jet in that event was seen in gamma rays.
So Rasmik showed an illustration of the first cosmic neutrino detection of supernova 1987A, and we didn't have gravitational wave detectors at that time. So it's all just coming together as the technology increases and we have more opportunities to do these multi-messenger.
So we have a few minutes. There it is. We have a few minutes before we end here, and so Justin and I thought it would be good if anybody has any questions here that we can answer. Obviously, the YouTube will continue on, and you can watch it. Just look up the NSF, IceCube, and Neutrino, and you will find the YouTube link. Also, there's going to be a hashtag, right, coming up, and a Reddit session. So do you want to say something about that, Justin, Reddit?
Yeah, for those of you interested in Reddit or your friends who are non-scientists, starting at 11:30, Ali Kirandesh here and I will be taking questions on Reddit along with several of our partners from the other observatories that you saw here. So any questions from the audience? Yeah.
So why are neutrinos so damn difficult to see, and why are they so reluctant to interact?
That's yours, Justin.
Okay, I'll take that one. So one of the fundamental reasons is that they don't have any electric charge. So the same reason that they're not deflected by magnetic fields like the protons are, they don't participate in the electromagnetic interaction. So in physics, we quantify that as a cross-section. That means that they have a very tiny cross-section. So they basically can travel through the entire Earth, even many Earths, with a very small probability of hitting anything. That's why you need such a huge detector.
Yeah. Is the probability of detecting in IceCube a function of the energy, and therefore you're going to detect a higher flux, which isn't necessarily a higher flux, but a higher flux of very high energy?
Yeah. That's a great question. So the question was, is the probability of interaction a function of energy? Yes, it is. It's a strong function of energy. So at the highest energies where we're detecting neutrinos, it actually does have a reasonable chance of interacting in the Earth. In fact, at the highest energies, at about 10 to the 15 electron volts, it cannot travel through the entire Earth. So the statement about traveling through the entire Earth is true of lower energy neutrinos. We actually see at the very highest energies that the Earth can absorb neutrinos. But there are two competing effects. So you have this increasing probability of neutrino interaction, and yet you have a steeply falling distribution of the neutrino energies, of the astrophysical neutrino energies. That plot that I showed earlier was actually scaled by energy squared. And so you multiply these two, one dropping, one increasing, and you get the distribution of the energies of the detected events in the detector.
Eric?
So now we know that there are protons in the jets. I'm going to ask a greedy question. Is there any reason should we, to zeroth order, think that the distribution of protons and electrons in the jets are equal? In other words, you get charge neutrality from the two of them? Or is there any indication as to whether there might be a mix of protons, positrons, and electrons? I'm just wondering how we should think about jets now.
So let me try to answer that by showing you something that illustrates the problem right here. This is the energy distribution from a blazar. And I think it was 3C279, but I don't remember for sure. The solid line is a model with protons in it, and the dashed line is a model with, so here's the solid line, the dashed line is a model with protons in it. So you have protons and you have a pure hadronic model. And so you have an leptonic model, which is just light particles and dashed, and you have one with protons in it is the curve. The differences are very small. So the first problem of how many of them have protons really only can be answered as you get more neutrino detections, because you can make models of the two that are, at least in the present time, close enough, given our data, that you can't tell the difference. There are some clever things you can do to make measurements to tell the difference, but they're very subtle and it's very, very challenging. On the other hand, the other side of the thing I think I should mention is if there are protons in there, then these jets are much more energetic than we realized. It does up the energy by factors of what? Remember, Justin?
So one way to quantify that is the total power in neutrinos compared to the total power in gamma rays, right. And we think there's about a factor of a few more power in the neutrinos than in the gamma rays for this particular object.
Right, right. So you multiply that times some efficiencies. You're probably talking factors of few to 10, something like that. So it does change what we think about jets. But remember, in astrophysics, sometimes you think things are the same and they're not. And the reason that they're not is you've observed only one aspect or one facet of the system. And this could very well be one of those cases where we've been observing the electromagnetic signature and therefore missing the main show, which may be the hadronic part of the jet. We just don't know yet. But here's the first hint. It's a major change in how we look at things.
Ken?
Can you comment on blazars and when they either change energy or frequency in the electromagnetic spectrum, and perhaps how that could relate to this quantity? Is it, suddenly some big star, some more hadrons accreted on and then get spewed out, and so you get more neutrinos associated with versus that? Does that fit?
I guess I'm going to get stuck with that one. I think maybe the key thing, there is some expertise, some people in my department who know more about this than I do, like Sebastian, who's sitting there silently. So let me get a try at it. The thing we realize from the very short time scales of these events is that it's occurring in a region within a few light months, less than a light year, of the center of the galaxy. Exactly how the different flaring events relate to the production of particles isn't clear. One can think of models where you accrete something that has a lot of hadrons in it, like you swallow a star, and that this then changes the nature of the jet during a flare. But are all flares like that? Probably not. Some of the flares are like sparkles, where you line up with some of the relativistic material. When you line up right at you, it gets brighter. I turn it away, it gets dimmer. So there may be multiple kinds of things going on here. What this does is it adds a new dimension and really makes it a very serious business to understand how the hadrons get in. And by the way, since protons are charged particles, the magnetic fields are huge in jets, the energy densities are high, the protons can also radiate. And once you start putting that in, you have another handle on what's going on, but one that's not easy to disentangle.
I could just add a little bit to that. There are actually two different interesting time periods, just to clarify if it wasn't clear to everyone here, of emission from this particular object. So in 2017, September, there was the coincidence between gamma rays and the neutrino. That's exciting. But also in 2014 to 2015, for a few months, there was neutrino emission, a flare of neutrino emission alone that was not accompanied by a gamma ray flare. And so that's an interesting surprise, and that's kind of underlining this fact that neutrinos and gamma rays really carry complementary information. And so we need to keep building up all of this different types of information, putting it all together into a coherent picture.
And I should point out that with the enhanced capabilities of IceCube, then we expect to be able to get more detections. And when things are time dependent, and you have always the tip of the astrophysical iceberg is always a very, very difficult problem. Is the iceberg just a skim on top of many blazars? Or, this can happen, is there one up here and the next one's a factor of 10 down? That's what makes life interesting.
Yeah.
So I have a related question. I mean, was there anything unusual about this source as a blazar before it was discovered to have these neutrinos?
So if you think of it, so it's a gamma ray detected blazar. There are thousands of gamma ray detected blazars in the GeV energy range, 100 on the order of 100 in the TeV energy range. This was not known yet in the TeV energy range before this event. Among GeV detected blazars, it is among roughly the brightest 1%. So that's kind of interesting. However, there are other brighter ones in gamma rays that we have not detected. So again, it's a complex picture combining different pieces of information.
How sensitive is IceCube? Like, if there is a neutrino collision in the detector, is there a chance that you would miss it?
If there's a neutrino collision inside the detector, is there a chance that we would miss it? Not as long as it's energetic enough. There are some that are even lower energy from the sun, for example, that are traveling through the detector all the time. Some small fraction of them are colliding inside the detector, interacting. Those lower energy ones we miss. But as long as they're high enough energy in the TeV to PeV energy range, we will detect them. And some of them down even in the GeV energy range.
Sebastian?
Do you know anything that might be particular about the host galaxy?
We don't know anything about the host galaxy except there's a little bit of a bias. Here's another astrophysical thing. There are many, many blazars. But when this one became important, people really put the pedal to the metal in terms of observing it. And as a result of that, it's some of the best optical spectra ever obtained. So we see very, very weak emission lines showing that it does have a host galaxy. That's how we got the redshift. But the host galaxy isn't resolved. The contrast is very high. So we don't know much about the host at all. The problem with this is that this blazar is at relatively low redshift, 0.37, right? Approximately.
Yeah.
And so basically, we don't know how many others are at this kind of situation because nobody has been able to invest the time to get similar measurements to determine if there's a population of these things. So it could be a uniquely powerful nearby blazar, or it could be the tip of some kind of a distribution of blazars. But beyond that, we don't know. And just so the audience can see, I actually have a picture very quickly here. You want to say something while I wander around in my pictures here?
Well, it's a relatively far blazar for its brightness. So that's another interesting piece of the whole puzzle.
So here's what it looks like on the sky. There are two stars and the crosses on the blazar. Very spectacular. It looks just like a star. And here is the problem, which you can see. On here is an image with a telescope. This is a blazar. Here's the model of the point spread function of the galaxy, and here's the residual showing the point source in the center. And the point is that the galaxy, the blazar, is so bright, this is a star, that it almost hides the galaxy. It's extremely difficult to dig out the galaxies under blazars. But usually they're elliptical or early type galaxies without a whole lot of gas in them. That, by the way, means the target making the neutrinos is most likely light particles, photons, inside the jet.
Yeah.
So there was I guess there was a 2014 flare, right, of this event. Have there been other neutrino flares observed in the data going back?
From this event or more generally?
Just all across the sky
Okay.
at the time.
So one of the things we do in IceCube is we search, like I showed you that map, we search for individual discrete sources around the sky. We can do that by combining all of our data from 9 or 10 years of observing. But we can also look at each point in the sky for whether there's been an excess, a short duration excess. We've done that analysis previously and we never found any. The challenge with that analysis is you have to scan over lots of points on the sky, lots of times of when the emission could have been, and even lots of durations of when it could have been. So you have this huge trials factor, and so that dilutes your sensitivity. Once we knew a particular direction on the sky with an interesting source, we did this time-dependent analysis in that particular direction, and we saw this evidence. But we have not seen any for any other directions on the sky yet.
Can you say what the statistical significance is for the spatial temporal correlation?
Yeah, so there are really 3 different lines of evidence. So there's the 2017 September high-energy neutrino event, coincident with a flaring GeV and TeV blazar. That's one. There's then going back in the historical data, there's this evidence for a flaring neutrino source in 2014 and 2015 for a few months. And then there's also just stacking together all the data from that particular direction on the sky. In 9 years of data, there's also evidence for kind of average emission from that direction in the sky. So the sort of the false coincidence rate, if you think about, well, there are IceCube alerts at various times in different directions. There are a lot of blazars on the sky, several thousand. So what's the probability that one could have just by chance happened to be in the same direction as the neutrino flare, as the neutrino alert? That's about 3 sigma sort of significance. If you then look at the other 2 analyses that I mentioned, the neutrino flare 2014 to 2015, that's about 3.5 sigma significance. And then if you look at the neutrino steady point source analysis, that's more like 1% p-value. So they're all interesting. They're all at the 2 to 3 to 4 sigma level, but there's several different lines of evidence, each with interesting indication. It doesn't rise to the 5 sigma threshold that we have in particle physics, for example, but it's several independent lines of evidence that are very exciting.
Can you combine those probability spaces in a way to get something out of it?
We had a big debate about whether to do that or not. We decided not to for now because it's 3 very different lines of evidence, and so we presented them as they are. Other people can choose to combine them if they like to. It's a little bit of subtle statistics in terms of what you treat as independent versus not independent.
Shall we call it close so you can run over and do the Reddit?
Yeah, we have until 11:30 for that, so I'll stick around. I think Jay might for a few minutes.
Yeah, we'll stick around for informal questions if anybody has
I also just want to mention there are a lot of IceCube members here in the audience.
Yeah, why don't you have them stand up?
Yeah.
Yeah. No, stand up. Stand up. Let's so we can see.
So they're. So we have professors here, undergrads, grad students, postdocs, scientists, engineers. So a lot of them can answer your questions as well.
And please tweet Facebook, Blazar Jets. That's